So far, we have discussed about the problem of natural frequency, right? And we solved few problems on that. Now, we will discuss 2, 3 different cases again based on natural frequency. As I explained earlier, that natural frequency is basically important for free vibrations, right? So we need to discuss more and more cases in that case, right? Now, here again is one more cantilever beam, right? Okay. Now, the previously cantilever beam, which has been discussed in last series, was having a weight at its free end only. Now, this arrangement is slightly different. Suppose a spring is attached right here, and here is a mass m, right? And a spring is have a stiffness of k, and beam is having a length of L, and the flexure rigidity of this beam is given by EI. I hope you are familiar with that term. EI represents flexure rigidity, E is the Young's modulus, and I is the area moment of inertia of the cross section of beam. Now, the first point of discussion is that this particular part, right? As in the last cantilever case, we said that in that case there is a particular stiffness of beam is there, and another stiffness involved is this uh, spring stiffness, right? Now, our I mean this particular case is of parallel arrangement of springs or series arrangement of strings. Now we need to go to that basic definition. That time I explained that in parallel arrangement, the deflection should be equal of whatever be the springs we are considering. Right now, if we considering the unequilibrium condition when this load get its effect, firstly the beam will come down, and then the uh, spring, right? So the net deflection of mass is sum of this spring's extension and that amount by which beam will come down. So clearly net deflection is summation of these two terms. Since it is summation of these two terms, so this case is particularly of series type case, right? Now the problem has become very easy since we have identified that this is a case of series, right? So now the application has become very easy. Okay. Now the beam's stiffness, as I explained earlier, I'll explain it one more time. The deflection in that case, when it is subjected to a free end load, this is mg L cube by 3I. This is the formula which we have got from strength of material, right? Beam's deflection theory. Now, this stiffness, as I explained earlier, K beam is equal to mg by delta, which is load upon deflection. It represents 3ei divided by L cube. The another stiffness involved in the system is that this K, right? Now, as I said, this is a parallel arrangement. So the K equivalent of the system, which is equivalent to stiffness, is 1 upon K of this spring and plus 1 upon K beam, right? Putting the value in this equation, we will have 1 over K plus 1 divided by 3ei and L cube, right? So far so good. Upon solving, we will get 3ei K is equal to 3ei plus K L cube, which is equal to 1 upon K equivalent. So therefore our K equivalent is 3ei K divided by 3EI plus KL cube. Now, we are looking forward for natural frequency here. So, omega n is what? Under root K equivalent divided by M. Right? So, this is by putting this value inside this square root, we will get our equation or value of natural frequency for this particular system, right? So the main issue in this sort of problems is that we need to identify firstly the parallel and the series case. Then the problem will become very easy since we have already cleared the concept of getting stiffness for different cases in the previous series. Now let us take one more example. Suppose there is a cylindrical bar has been dipped inside a liquid of density, let us say it is rho, right? Diameter of this particular section is d, mass of this bar is m, right? Now, so similar problem, we again have to determine the natural frequency when this particular cylinder is slightly depressed inside the water. I mean, this particular condition is of equilibrium, right? When it is slightly depressed, let us say a distance x, and released then, which is a quite practical case you might have experimented in your childhood. So we just depressed this bar inside the water by distance x, then released so that buoyancy will help it to come up, right? Now, so for that particular case, we need to determine the uh, natural frequency. Now, we need to see this while this situation is of equilibrium, then the weight of this cylindrical bar is been balanced by the buoyant force, and the buoyant force is how much? Let us say the length of this particular bar is L. So here we have the volume of this bar is pi by 4 d square L, right? And buoyant force is G. So if this situation holds, the bar will remain stationary, right? When I said that this particular thing bar is depressed inside the water, by depression the length, right? This has been a little mistake here, this representation, right? L is the immersed length. L length is the immersed length, right? So this particular force will give us buoyant force. Now, if x length more, it is depressed by x distance. So now L plus x length inside the water, right? Now we will use Newton's second law, since we said that while the L length of this particular bar inside the water, it is in balance equation. While we are trying to depress it more, it releases and comes up into motion until and unless the equilibrium is established. So Newton's second law will come into picture. Newton's second law says that mx double dot, and the restoring force again is the buoyant force, which is again pi by 4 d square. Now the length inside is L plus x, and disturbing force is mg, which is equal to 0, right? Now by this first equation we can get this mg should be equal to pi by 4 d square L into rho into g. Now the few terms have been defined here. This is rho into g. So this equation will become mx double dot plus pi by 4 d square x rho g is equal to 0. As I explained earlier that mx uh, sorry in, we need to modify it a little more to compare with the standard equation. It will come out as x double dot plus pi d square rho g divided by 4m into x equal to 0. Now the standard equation, a standard differential equation in this case is x omega n square x is equal to 0. So we get the expression of omega n as pi d square rho g divided by 4m, right? So this is how we, in a particular fluid problem, this kind of vibrational aspect can be derived. Right? This is a very small example, but we can learn a lot from it, right? Now I would like to introduce one more problem which involves the rotational part, right? Which is till now I guess we got only one problem, one cylindrical problem on an inclined plane, which depict the rotational energy involvement. But let us discuss one more problem based on rotational part. Right? I hope this has been clear to all of you. Okay. Now, see, this is some kind of pulley arrangement which has been fixed at center. Right? One side, with the help of rope, there uh, uh, one spring is attached, right? Which has a stiffness of K. This pulley is having of mass m and its radius is r, and this particular thing is of mass small m. Now, similar situation, a deflection of x is given. Right? This again can be done by the Newton's second law implication, but the convenient method in this case is uh, the energy method. Now, what kind of energies are involved in this? It's like the energy of the system, which will remain constant, which is essentially our energy theorem. Now, the first energy, the representation again, x represent displacement, x dot is velocity, and x double dot is acceleration. So the kinetic energy is given by half mv square, and we are representing velocity by x dot, so this half mx square. Again, plus one rotational energy of this pulley system because mass is considerable. So half I omega again how much x dot by r square plus the potential energy of the spring is half k x square. Right? Now these three energies are involved and the summation is constant. Now upon differentiation we will get m x dot x double dot, right? The double differentiation represented by double dot plus the moment of inertia of this pulley is mr square by 2, and this is 1 upon r square, and again we have x dot plus x double dot plus half, sorry, not half, k x dot equal to 0, right? So here we got, this got cancelled, m plus m by 2 x double dot plus kx is equal to 0. Again, with the standard equation we need to make it x dot plus k upon m plus m by 2 x is equal to 0. Again, comparing with the standard equation, which is x double dot plus omega n square x equal to 0, we will get here omega n is equal to k upon m times m by m plus m by 2. This is our natural frequency, right? Sometimes they generally ask for frequency only. This is basically angular frequency. When they ask for frequency, which unit is per second or per unit time, so omega holds a relation is 2 pi f, which is only frequency, what we have discussed in the basic terminology in very beginning, right? And if we need to find out the time period, the oscillation time period, so f is equal to 1 upon t. Now we can convert this formula directly. F is equal to 2 pi by t. So by using this natural frequency, we can find out different systems time period also, right? But the basic step will start from determining the natural frequency, and it certainly have many implications in that part, right? Okay, so here we are ending this natural frequency session, and after that we will try to justify these different kind of motions based on their natural frequency analysis in case of free vibrations, undamped frequency system, right? So we will involve damping later on, and we'll discuss their cases separately. So far we have only a spring in all those systems we have discussed, right? So we will now move towards the damping and discuss more about the uh, how damping affects the motion, and certainly it also affects our natural frequency as well. Now the natural frequency will turn around to be the damped natural frequency. It will affect our damping also. Thank you very much.